We are on the verge of seeing the atmospheres of alien worlds. This is the new frontier of space exploration, a reality built by 25 next-generation missions that will fundamentally reshape our cosmic understanding. By the end of this journey, you will know which projects could find life, probe dark matter, and listen to the birth of the universe. We will uncover how a drone will fly on a moon of Saturn and what a space telescope 1,000 times more powerful than Hubble might see. What single discovery would most change your perspective on our place in the cosmos? A profound stillness surrounds a distant star, a place where a world much like our own might be orbiting in the gentle warmth of its habitable zone. For the first time, we are building the tool that could not only find that world but study it in stunning detail. The Habitable Worlds Observatory represents a quantum leap beyond even the James Webb Space Telescope. Its primary mission is to directly capture the light of Earth-sized planets, a feat once thought to be the stuff of science fiction. It achieves this with an advanced instrument called a coronagraph, a device that acts like a sophisticated thumb blocking a brilliant flashlight. By precisely blotting out the overwhelming glare of a parent star, this observatory reveals the faint, steady glow of a small, rocky world right next to it. What was once a hidden speck becomes a full-fledged world for us to analyze. Scientists will then dissect that faint light, spreading it out into a spectrum that reveals the chemical fingerprints of the planet's atmosphere. They will be searching for key biosignatures, gases like oxygen and methane that, in certain combinations, could strongly suggest the presence of life. But the ambition goes even further. This observatory might be able to discern surface features, telling us if a planet is a dry desert, a global water world, or even one with distinct continents and oceans. This transforms the search for life from a theoretical exercise into a direct investigation. We are no longer just counting potential planets. We are beginning to study alien environments for signs of a living biosphere. The question of whether we are alone in the universe is on the verge of being answered not by chance, but by deliberate, profound observation. This incredible power to see other Earths directly leads us to missions that listen for them, tuning into the faint whispers of the cosmos itself. While we learn to see the atmospheres of alien worlds, a different kind of observatory is being built to listen to the cosmos. Picture a perfect triangle of 3 spacecraft, each separated by 2.5 million kilometers, tracing an endless orbit around the Sun. They are connected only by beams of laser light, forming the most sensitive measuring device ever conceived. This is the Laser Interferometer Space Antenna, or LISA, and its mission is to detect the faintest whispers in the fabric of reality itself, the ripples in space-time known as gravitational waves. Ground-based observatories have heard these cosmic chords, but they are like listening to the roar of a nearby stream. LISA will hear the deep, resonant hum of the entire ocean, the low-frequency waves generated by the most massive events in the universe. It will tune into the final, swirling dance of supermassive black holes as they collide and merge at the centers of galaxies, events that shake the very foundations of space-time. Lead scientist Dr. Carsten Dansman describes this not as seeing the universe, but as hearing it. This new sense allows us to trace the hidden growth of galaxies and to test the limits of Einstein's theory of relativity in environments of unimaginable gravity. By mapping these cosmic tremors, LISA will reveal a universe largely invisible to traditional telescopes, uncovering the dynamic choreography of space-time. As we learn to listen to the cosmos, we also prepare to send robotic emissaries to touch and taste alien worlds for ourselves. A thin, fractured crust of ice stretches to the horizon, hiding an ocean containing more water than all of Earth's seas combined. NASA Europa Clipper is the first mission designed to fully investigate this alien world, a moon of Jupiter that challenges our very definition of a habitable place. This sophisticated spacecraft will not orbit Europa directly. Instead, it will perform a daring series of close flybys, at times swooping a mere 25 kilometers above its enigmatic surface. On each pass, a suite of powerful instruments will act as our remote sensors. An ice-penetrating radar will send signals deep into the shell, mapping its hidden structure and measuring its thickness for the first time. A thermal imager will scan for warm spots where warmer water from the deep ocean might be welling up to the surface, while a mass spectrometer will taste the tenuous gases and particles ejected from the moon, analyzing their chemical makeup. The primary goal is to understand Europa's potential for life. As project scientist Dr. Robert Pappalardo explains, the mission is not about finding life itself, but about determining if this distant ocean world possesses the three essential ingredients. We know it has abundant water and likely a source of heat from the tidal forces flexing its interior. The final, crucial piece is chemical energy. Does the ocean floor host hydrothermal vents, and does the water contain the complex chemistry needed to sustain living organisms? By meticulously mapping the surface and subsurface, Europa Clipper will identify not only the most promising locations for a future lander, but also the safest places for it to touch down. This mission is the essential scout, paving the way for a subsequent mission that might one day drill through the ice and directly sample the ocean beneath. The secrets preserved in Europa's deep freeze could tell us that life is not a rare accident, but a cosmic imperative. This search for life's ingredients in our own celestial backyard compels us to look even further, to missions that will dissect the very dawn of time. While Europa Clipper studies a hidden ocean, another mission will fly through the thick, orange skies of a world that resembles a frozen, primordial Earth. This is Dragonfly, a revolutionary rotorcraft destined for Saturn's moon Titan. Imagine an 8-rotor drone not navigating the thin air of Mars, but soaring through an atmosphere 4 times denser than our own, allowing it to fly with remarkable ease between sites dozens of miles apart. It will land on vast dunes made not of sand, but of organic particles that rain from the sky, and on water ice bedrock that acts like stone. This is not a stationary lander. It is a mobile laboratory capable of exploring diverse environments across this alien moon. Its suite of instruments is designed to sniff out and analyze complex organic molecules, the very chemical building blocks that, under the right conditions, can lead to the emergence of life. Principal investigator Dr. Elizabeth Zibai-Turtle calls Titan a natural laboratory, a place where we can observe the same kinds of chemical processes that occurred on Earth before life ever began. With its methane lakes and ethane clouds, Titan presents a profound analog to our own planet's early years. By flying from one site to another, Dragonfly will be able to study how these prebiotic compounds form, interact, and evolve in different geological settings. This mission represents a fundamental shift in how we explore other worlds, moving from single-point observations to agile, targeted reconnaissance. The ability to travel across such a dynamic and chemically rich landscape gives us our best chance yet to understand the steps that lead from simple chemistry to the complex dance of biology. This quest to understand our own origins by touching alien worlds leads directly to an even more audacious endeavor, one that aims to bring a piece of another planet back to Earth. A capsule streaks through the atmosphere, its heat shield glowing against the dawn sky before a parachute deploys, guiding it to a gentle rest on the desert floor. Inside are the first samples ever deliberately retrieved from another world. This is the culmination of the Mars Sample Return Campaign, a decades-long ambition now becoming a breathtaking reality through an unprecedented partnership between space agencies. The Perseverance rover has already done the hard work, carefully selecting and sealing tubes of rock and soil from an ancient river delta, a site on Mars that once held water and could have been hospitable to life. But the true scientific revolution begins when those pristine samples are opened in the most secure laboratories on Earth. There, scientists will deploy instruments the size of rooms, tools far too large and complex to ever fly to another planet. They will examine the material atom by atom, searching for microscopic textures or complex organic molecules that could serve as definitive evidence of past life. Beyond the search for biosignatures, these rocks hold a detailed record of the Martian climate's shift from a warm and wet world to the arid desert we see today. This is not just about retrieving rocks, it is about unlocking a planetary autobiography, one that can tell us about the evolution of all rocky worlds, including our own. The engineering to make this happen is a monumental dance of precision. It requires a new lander to touch down, a rocket to launch the samples from the Martian surface, and a spacecraft to capture that precious cargo in orbit and then carry it home. The success of this intricate cosmic choreography will provide a geological treasure that will be studied for generations, fundamentally shaping our plans to one day send human explorers to the Red Planet. While we prepare to bring pieces of Mars home, another mission is already on its way to a world made not of rock but of metal. A field of view 100 times wider than Hubble's will soon scan the heavens, not to focus on a single celestial wonder, but to conduct a grand cosmic census. The Nancy Grace Roman Space Telescope is an observatory built for scale, designed to map the structure of the universe itself. Its primary mission is to investigate the most perplexing force in cosmology, the mysterious dark energy that is causing the expansion of our universe to accelerate. By measuring the precise distances and positions of millions of galaxies across vast stretches of space and time, Roman will trace the history of this expansion with unprecedented detail. It will study how the largest structures in the cosmos, immense filaments and voids of galaxies, have assembled over billions of years. This grand map will allow scientists to test competing theories about the nature of dark energy, determining whether it is a constant force or one that has changed over the life of the universe. Dr. Dominic Benford at NASA Goddard explains that the telescope will also uncover thousands of new worlds beyond our solar system using a clever technique called microlensing, which detects planets by observing how their gravity bends and magnifies the light of distant stars. Its wide field of view will perform deep infrared surveys, peering through cosmic dust to reveal a sky teeming with data. This mission provides the foundational context for everything we see, charting the distribution of both dark energy and the invisible dark matter that shapes the cosmos. By creating this ultimate map of the modern universe, Roman sets the stage for a mission that will look back to the very beginning, to capture the first light of creation. A new kind of map is being drawn, one that charts the cosmos not just by the positions of stars and galaxies, but by their very chemical essence. The SPHEREx mission will scan the entire sky in 96 distinct colors of infrared light, creating a cosmic fingerprint for hundreds of millions of celestial objects. Each point of light in this vast survey will be broken down into its unique spectral signature, revealing the hidden composition of distant galaxies and the nascent stars within our own. This immense data collection aims to answer two of the most profound questions we can ask. First, by meticulously mapping the distribution of galaxies across the universe. Scientists will search for faint, fossilized imprints from the inflationary period, that moment of unimaginably rapid expansion just after the Big Bang. This could reveal the fundamental physics that set the entire cosmic stage into motion. Second, SPHEREx will turn its gaze inward, toward the dense, cold clouds where new stars and planets are being born. There, it will detect the subtle spectral features of water ice and complex organic molecules frozen onto dust grains. This is a direct census of the raw ingredients for life, allowing us to measure how common these vital compounds are throughout our galactic neighborhood. The mission's project scientist, Dr. James Bok, describes this as moving from simply knowing these ices exist to understanding their abundance and distribution in different stellar environments. The resulting three-dimensional chemical map of the universe will be a treasure trove for a generation of astronomers, revealing the physical processes that govern the evolution of cosmic structures. This grand, all-sky chemical survey provides the context for missions that will then focus with laser precision on the most dynamic and violent events in the universe. An invisible, searing heat defines the true architecture of the cosmos, a universe woven from filaments of million-degree gas and illuminated by the furious energy of matter plunging into oblivion. The Athena X-ray Observatory is our first dedicated window into this hidden, high-energy reality. Led by the European Space Agency, this telescope is engineered to see the X-ray glow from the first supermassive black holes to form after the Big Bang, tracing how they grew and fundamentally shaped the galaxies around them. It will map the vast reservoirs of hot gas that are strung along the cosmic web of dark matter, observing the physics of galaxy clusters, the most massive gravitationally bound structures in the universe. Professor Kirpal Nandra notes that Athena will transform our understanding of how the hot universe works, probing the very edges of black hole accretion disks where space and time are twisted beyond recognition, and studying the colossal winds blown out by supernova explosions. Its high-resolution X-ray vision is like moving from a blurry snapshot of a distant fire to having a microscope that can analyze every single ember. This allows it to dissect the aftermath of the most cataclysmic events, from the furious flares of distant stars to the chaotic debris left behind when two neutron stars collide, events that forge the heavy elements essential for planets and life. By charting this violent, energetic cosmos, Athena reveals the forces that build and destroy the largest structures in existence. To fully understand the universe, we must also learn to detect the unseen scaffolding that holds it all together. A silent constellation of 4 spacecraft will drift in formation, their combined gaze focused on a single, distant star. This is the Darwin mission, a flotilla designed not just to find other worlds, but to literally sniff the air of those that resemble our own. The technique they will use is as brilliant as it is delicate, a process called Nulling Interferometry. By flying in a precise formation and combining their collected starlight, these observatories can act as a single, giant virtual telescope. Their synchronized light waves are tuned to cancel each other out, effectively erasing the overwhelming glare of the central star. What remains is the faint, tranquil light reflected from the small, rocky planets orbiting within the habitable zone. That captured light is then spread into a spectrum, a chemical barcode that reveals the precise composition of the planet's atmosphere. Scientists will scan these spectral lines for the telltale signs of key gases, particularly the dynamic duo of oxygen and methane. On Earth, these two gases are in a constant dance, rapidly reacting with one another and disappearing from the air unless they are continuously replenished by living processes. Finding them together in an exoplanet's atmosphere would be a powerful, though not definitive, suggestion that a biosphere is at work. The mission would also look for ozone, a byproduct of oxygen and carbon dioxide, completing the picture of a potentially life-sustaining world. The stability required for this is almost beyond comprehension. The spacecraft must maintain their positions to within a fraction of a millimeter over vast distances, a feat of engineering that makes this one of the most ambitious scientific endeavors ever conceived. A detection by Darwin would not be a single, loud announcement of life, but rather a quiet, repeated, and statistically robust measurement. It would provide the first compelling evidence that we are not alone, that the chemistry of life is a phenomenon that exists beyond our pale blue dot. This profound step from discovering planets to diagnosing their living potential forces us to ask what other fundamental forces remain completely unseen, shaping the cosmos from the shadows. Orbiting the Moon, a small, modular station will become humanity's first permanent outpost beyond the familiar embrace of Earth. This is the Lunar Gateway, an international collaboration that transforms the space between our world and its moon from a void to be crossed into a place to live and work. Far more than just a space station, Gateway will serve as a versatile hub for astronaut expeditions, a unique scientific platform, and a critical testbed for the technologies we will need to survive the long journey to Mars. Its managers describe it as a staging point, a reusable waypoint that fundamentally changes the economics and safety of deep space travel. Instead of launching a single, massive mission directly from Earth to the Martian surface, future crews could assemble and provision their interplanetary vehicle at the Gateway, using it as a port of call. This orbital command post will host a suite of instruments specifically designed to study the harsh environment of deep space, particularly the intense solar and cosmic radiation that poses one of the greatest risks to human health on long-duration voyages. By monitoring this radiation and testing new shielding technologies in a real-world setting, we gather the essential data needed to protect astronauts on their way to Mars. The Gateway will also serve as a communications relay and a coordination center for complex surface operations on the Moon, enabling more ambitious robotic and human exploration of the lunar South Pole. There, in permanently shadowed craters, we will learn to live off the land, practicing in situ resource utilization by extracting water from the ice to create breathable air and rocket fuel. This ability to harvest local materials is the key to sustainable exploration, turning a distant destination into a place where we can truly put down roots. The Gateway is not merely a destination. It is the foundational piece of infrastructure for an interplanetary highway, a bridge built in the silence of cislunar space that will ultimately carry us to the Red Planet and beyond. As we construct this stepping stone into the cosmos, we must also develop the tools to see the universe with a clarity that defies belief. A car-sized camera will soon begin photographing the cosmos, capturing the most profound motion picture ever made. The Vera Rubin Observatory's legacy survey of space and time is not a telescope built to stare, but to scan, recording the entire visible southern sky every 3 nights for an entire decade. This relentless observation will produce a time-lapse of the universe on a scale we have never seen, revealing a cosmos in constant, dramatic flux. Each snapshot will contain billions of galaxies and stars, and by comparing one image to the next, scientists will track everything from the subtle drift of asteroids to the violent flare of supernova exploding in distant galaxies. Director Dr. Stephen Kahn describes this capability as a microscope for the cosmos, a tool that makes the invisible dynamics of the universe starkly visible. Its primary power lies in this comprehensive monitoring, allowing it to catch transient events that would otherwise be missed, events that blink into existence and fade away in the cosmic darkness. One of its most immediate and practical roles will be to catalog the millions of small rocky and icy bodies orbiting in our own solar system, building a detailed map of our celestial neighborhood and identifying any potentially hazardous asteroids on paths that bring them near Earth. But its deeper mission is to probe the invisible architecture of the cosmos. By observing how the light from billions of distant galaxies is subtly warped and distorted as it travels to us, the survey will map the distribution of dark matter, the unseen scaffolding that shapes the universe. It will also trace the accelerating expansion of space driven by dark energy, not by looking at one galaxy, but by tracking the statistical motion of countless millions over time. The data stream from this endeavor is almost beyond comprehension, expected to grow to over 60 petabytes, a digital universe that will fuel scientific discovery for generations. This new, dynamic view of the sky reveals a universe that is not static, but alive with fleeting events that scream for our immediate attention. A spacecraft waits in the silent darkness, a sentinel stationed a million miles from Earth. Its purpose is singular and profound: to remain on standby until astronomers spot a stranger approaching from the deep cold. This is the Comet Interceptor, a mission unlike any other, designed not for a predetermined target but for a visitor. It will spring into action upon the discovery of a long-period comet, an ancient wanderer falling into the inner solar system for the very first time, or perhaps even an object from another star. The Interceptor will then race to meet this pristine traveler, reaching it before the sun's heat has a chance to significantly alter its frozen surface. This is the crucial difference. Comets we have visited before, like the targets of the Rosetta mission, have been worn down by countless solar passes, their original chemistry baked away. The Interceptor's target is a virgin time capsule, a relic preserved in the deep freeze of interstellar space for over 4.5 billion years. By analyzing the composition of its ices and dust, scientists hope to find the original recipe for our planetary system, the unaltered ingredients that eventually coalesced into the Sun and planets. This mission could answer one of our most fundamental questions: did these primordial comets deliver the water that fills our oceans and the complex organic molecules that seeded life itself? To capture this fleeting opportunity, the mission employs a brilliant strategy. The main spacecraft will be accompanied by two smaller probes, released to fly much closer to the comet's dark nucleus. This trio will perform a synchronized dance, taking measurements and images from multiple vantage points simultaneously. They will build a holistic, three-dimensional portrait of the comet's structure, its gaseous coma, and its developing tail, revealing how such a pristine body awakens as it first encounters the warmth of our star. Catching a glimpse of this primordial messenger prepares us for the next logical step: missions that will not just observe small worlds, but physically touch them and bring pieces home. A cosmic forensic team is about to examine the scene of a carefully orchestrated crime. The European Space Agency's Hera mission is traveling to the Didymos binary asteroid system to perform a detailed post-impact analysis. Its target is the small moonlet Dimorphos, the very same asteroid that was deliberately struck by a DART spacecraft. While DART was the hammer, proving we could nudge a celestial object, Hera is the investigator arriving to document the full consequences. It will deploy a pair of tiny CubeSats to perform close-up reconnaissance, mapping the crater left by the impact with incredible precision. The main spacecraft will then use its suite of instruments to measure the asteroid's new mass, its altered orbit, and its detailed composition. This is not just about seeing the hole that was made. It is about understanding how the entire asteroid shook, recoiled, and redistributed its material from the force of the collision. For the first time, we will learn how a rubble pile asteroid, a loose collection of rocks and dust held together by minuscule gravity, responds to a high-speed impact. This data is the key to transforming a dramatic experiment into a reliable, predictable defense strategy. As lead scientist Dr. Patrick Mitchell explains, Hera's findings will turn this grand-scale experiment into a well-understood and repeatable deflection method. The mission effectively validates kinetic impact as a viable planetary defense technique, providing the essential physics we need to one day calibrate a response to a real threat. By confirming how much momentum is transferred in such an event, we move from hoping we can deflect an asteroid to knowing exactly how to do it. This capability to reliably nudge small worlds not only protects our planet, but also opens the door to future endeavors where we might one day guide resource-rich asteroids into stable orbits for study and use. This newfound control over our cosmic neighborhood compels us to look even deeper, to missions that will decode the very messages left behind from the dawn of time. Jupiter's immense gravity now holds a dedicated explorer, a spacecraft designed not just to visit the giant planet but to unravel the secrets of its most enigmatic moons. The Jupiter Icy Moons Explorer, or JUICE, embarks on a grand tour of 3 fascinating worlds, Ganymede, Callisto, and Europa, each a frozen sphere hiding a deep global ocean. This mission represents a systematic comparative study of alien water worlds, treating them as a family of potential habitats orbiting a single, colossal parent. Its suite of 10 advanced instruments will act as our remote eyes and hands, using radar to sound the depth of the icy crusts, lasers to measure surface topography, and magnetic sensors to probe the hidden, salty seas below. The sheer diversity of these 3 moons is what makes this mission so powerful. Europa, with its young, fractured surface, suggests a geologically active ocean. Ganymede, the solar system's largest moon, possesses its own intrinsic magnetic field, a unique feature that creates a miniature magnetosphere within Jupiter's own. Callisto, heavily cratered and ancient, presents a more stable, perhaps primordial, record of the early solar system. By studying all 3, JUICE will help answer why these similar environments evolved so differently. The mission's climax will be a first in human history, as JUICE breaks into a dedicated orbit around Ganymede. There, it will perform an intimate study of this complex world, mapping its surface of both dark, ancient terrain and brighter, grooved regions, while its magnetic measurements precisely gauge the depth and salinity of its hidden ocean. This is not merely about finding water, it is about understanding the full recipe for a living world. Does the ocean contact a rocky seafloor, allowing for the rich chemical exchange that fuels life at hydrothermal vents? Is the ice shell thin enough in places to permit material from the ocean to reach the surface? The data JUICE returns will build the most complete picture yet of what makes an ocean world truly habitable. This knowledge transforms our search for life beyond Earth, providing a detailed template for what to look for as we turn our next-generation telescopes toward the distant, icy moons orbiting planets in other star systems. The silent census of worlds has already begun. While mapping the grand structure of the universe, the Nancy Grace Roman Space Telescope will also conduct a profound headcount of planets, searching for them where other methods cannot see. Its microlensing survey peers toward the dense star fields at the heart of our galaxy, watching for a specific cosmic alignment. When a solitary planet, even a dark one, drifts directly in front of a distant background star, its gravity acts as a fleeting lens. This warps and magnifies the starlight, causing the faraway sun to temporarily brighten in a precise, telltale pattern. From this subtle flicker, astronomers can deduce the planet's mass and its orbital distance. This technique is uniquely powerful because it can find planets roaming the frigid outskirts of their solar systems, places where an orbit takes centuries and sunlight is a faint memory. It can even detect the most ghostly population of all free-floating planets that have been ejected from their birth systems and now wander the interstellar void alone. These orphan worlds drifting in perpetual night represent a class of celestial object we are only beginning to understand. The Roman telescope is expected to find thousands of planets through this method, building the first statistically complete demographic of our galaxy's planetary population. How many of these worlds are ice giants like Neptune or small, rocky bodies like Earth? The data will reveal the true diversity of planetary systems, testing our theories about how they form and why some migrate vast distances while others are cast out entirely. This galactic census fills a critical gap left by transit surveys, which are biased toward finding planets in tight, quick orbits around their stars. By revealing the full architectural range of solar systems, from the inner warm zones to the outer cold deserts, this mission provides the essential context for our search. It tells us which kinds of planetary arrangements are common and which are rare, ultimately guiding our quest to find those rare gems with conditions most reminiscent of our own pale blue dot. A faint whisper of polarized light holds the story of creation itself. Across the high deserts of Chile and the pristine ice of the South Pole, a new generation of telescopes like the Simons Observatory and the planned CMBS-4 are listening for a specific echo from the dawn of time, a subtle twist in the oldest light we can see. This light is the cosmic microwave background, the cooled and stretched afterglow of the Big Bang, and imprinted upon it is a unique pattern known as primordial B modes. Think of this as a fossilized imprint, a ripple in the fabric of spacetime generated during an unimaginably brief period called inflation, when the entire universe expanded faster than the speed of light. Finding this signature would be like discovering the first footprint of a cosmic giant, providing our first direct evidence for this foundational theory. Scientists describe this search as the ultimate goal of modern cosmology. It is a probe into a realm of physics we can never recreate, a window into energies so immense they dwarf anything our largest particle colliders can produce. Detecting this signal would not only confirm the inflationary epoch, but could begin to reveal how gravity itself behaves at the quantum level, unifying the very large with the very small. To find this whisper, these observatories must operate in some of the driest and coldest places on Earth, using detectors chilled to a fraction of a degree above absolute zero. Their task is one of supreme sensitivity, separating this incredibly faint primordial pattern from the glare of our own galaxy's emissions and the light of closer galaxies. It is an archaeological dig on a cosmic scale, sifting through layers of interference to uncover the pristine signature of the universe's first moment. The success of this quest would tell us not only how everything began, but could offer profound clues about how it will all end, connecting the first instant to the ultimate fate of the cosmos. This search for our universal origins leads us to a mission designed to find our literal beginnings, hunting for the chemical precursors to our own solar system in the dark clouds of interstellar space. The violent, high-energy infancy of the universe is a story written in X-ray light, a narrative we have only just begun to decipher. The Lynx X-ray Surveyor is a mission concept designed to read that entire epic, a telescope with a vision so profound it would see the first supermassive black holes ignite and trace the searing hot gas that built the earliest galaxies. Its collecting area would be hundreds of times larger than any current X-ray observatory, granting it a breathtaking sensitivity to the faintest whispers from the cosmic dawn. This is not merely an upgrade, it is a transformation in our perception, allowing us to witness the formation of the very first galactic structures when the universe was a mere few 100 million years old. Scientists describe Lynx as a time machine, one that would observe the energetic feedback from those primordial black holes, understanding how their powerful outflows either stifled star formation or catalyzed the birth of new suns. It would map the vast reservoirs of million-degree gas that reside within and between galaxies, the primary reservoir of normal matter in the cosmos, watching how it flows and cools to fuel new generations of stars. This high-energy perspective provides the crucial, missing context for the stunning images from the James Webb and Roman telescopes. While those observatories show us the stellar light and the distribution of galaxies, Lynx would reveal the violent, high-energy physics that actually govern their assembly and growth. It would peer into the immediate vicinity of black holes, probing the point of no return and testing the limits of Einstein's general relativity in the most extreme environments nature can provide. By charting the stellar life cycle in unprecedented detail, from the furious winds of young stars to the supernova explosions that seed the cosmos with heavy elements, Lynx completes our picture of a dynamic, evolving, and often violent universe. This deep look into the energetic forces of the past compels us to develop missions that can study the quieter, more mature galaxies of the present day, searching within them for the specific conditions that might give rise to life. The coldest, darkest places in the universe are often the most fertile. Deep within the frigid molecular clouds that drift between the stars, tiny dust grains become coated in a mantle of ice, a frozen archive of water and complex organic molecules. It is here, in this profound chill, that the story of a star system truly begins, and the Origins Space Telescope is conceived to read this frozen text. This observatory is a technological marvel, a massive instrument whose optics are cooled to within a few degrees of absolute zero. This deep cold is not a limitation, but its greatest strength, allowing it to perceive the faint heat signatures of the most distant and coolest objects, a universe of dust and birth that has remained largely hidden from our view. Its mission is to trace the water trail, following the journey of this vital molecule from the tenuous depths of interstellar space directly into the swirling protoplanetary disks where new worlds are taking shape. With its powerful spectrometers, Origins will act as a cosmic chemist, breaking apart the light from these dusty nurseries to identify the unique spectral fingerprints of countless molecules. It will map the distribution of water ice, carbon dioxide, and complex organics, creating a detailed inventory of the raw ingredients available at the very moment planets begin to coalesce. This allows us to move from simply knowing these building blocks exist to understanding their abundance and how they are delivered to young, rocky worlds. The telescope's revolutionary sensitivity also extends to the study of mature planets. It could directly analyze the atmospheres of Earth-sized worlds orbiting within the habitable zones of nearby stars, searching for the subtle chemical imbalances that might whisper of a living biosphere. By connecting the initial chemistry of a planetary system to its final, potentially life-bearing state, Origins offers a complete narrative arc. It seeks to answer whether the specific conditions that led to our own world are a common cosmic outcome or a rare celestial fortune. This profound investigation into our own chemical origins pushes us to look beyond our galaxy, to missions that will map the universe on its very largest scales. Our solar system is not an island, but a ship sailing through a galactic sea. For the first time, a mission is being designed not to visit another planet, but to leave our entire cosmic neighborhood behind. The interstellar probe is conceived as a 100-year voyage, a deliberate escape from the protective magnetic bubble our sun blows into space, known as the heliosphere. Its goal is to reach the untouched interstellar medium, the true, pristine environment of our galaxy. There, just beyond the heliosphere's edge, Its modern suite of instruments will perform the first dedicated analysis of this alien territory, measuring the density and composition of the plasma, dust, and magnetic fields that flow between the stars. This data is the missing context for our own existence, revealing the precise nature of the galactic wind that constantly buffets our solar system. The mission will also turn its cameras homeward, capturing an image of the entire heliosphere from the outside. This family portrait of our solar system would show the structure of this protective cocoon, illustrating how it shields all the planets from the harsh interstellar radiation. Scientists leading the project see this as the essential successor to the Voyager missions, which are now pioneering this frontier but with aging technology not designed for the task. The Interstellar probe would be built from the ground up for this one purpose, equipped with sensors to answer questions we did not even know to ask when Voyager launched. Its findings will tell us the shape and resilience of our celestial home, and by studying how the heliosphere interacts with the galaxy, we learn about the life cycles of other star systems and their potential to harbor life. This bold journey into the void is the necessary precursor, the final local voyage, before humanity one day contemplates sending its first robotic emissaries to the stars themselves. Deep within the Athena Observatory lies an instrument of almost impossible sensitivity, a heart that will feel the heat of the cosmos. The X-ray Integral Field Unit, or X-IFU, is a cryogenic spectrometer that operates just fractions of a degree above absolute zero. Its core is a microcalorimeter, an array of tiny pixels each capable of detecting the faintest whisper of energy from a single X-ray photon. Think of it as a cosmic thermometer, so precise it can register a temperature change of 1/1,000,000th of a degree. This phenomenal resolution allows the instrument to do far more than just see X-ray sources. It will perform a detailed chemical and dynamic analysis of the hottest matter in the universe. Each photon it captures carries a specific energy signature, a unique barcode that reveals not only which element emitted it, but also its velocity and the physical conditions of its environment. This transforms a brilliant but blurry image of a distant galaxy cluster into a rich, moving portrait. We will be able to trace the speed and direction of million-degree winds blowing from the vicinities of supermassive black holes, winds so powerful they can dictate whether a galaxy gives birth to new stars or falls silent. The instrument will map the circulation of heavy elements like iron and oxygen, forged in supernova explosions and then scattered by these galactic hurricanes, seeding future generations of stars and planets. For the first time, we will measure the turbulence and the subtle motions within the vast clouds of superheated gas that fill the spaces between galaxies in a cluster, understanding how this plasma cools and flows over billions of years. This is not merely observation, it is a direct interrogation of the physics governing the most extreme events in nature. The data from X-IFU will test the predictions of general relativity in the warped space just outside a black hole's event horizon and probe the fundamental laws of thermodynamics in cosmic laboratories we can never recreate on Earth. This ability to diagnose the physics of the invisible universe finds a powerful parallel in missions designed to see the unseen structure of everything. Two paths now diverge in our cosmic quest, each offering a radically different future for how we search for life. On one side stands the concept for LUVOIR, a telescope of almost unimaginable power with a segmented mirror that could be over 15 meters across. This instrument would not just be a successor to the James Webb Space Telescope, it would be a universe-transforming observatory, a versatile tool for every corner of astrophysics. It could directly image and analyze the atmospheres of Earth like exoplanets, while simultaneously probing the formation of the first galaxies and the structure of cosmic dust. Its ambition is to do everything to be the ultimate all-purpose eye on the cosmos. The alternative is HABEX, the Habitable Exoplanet Observatory, which takes a more focused surgical approach. Its primary goal is singular and profound, to directly photograph dozens of the most promising Earth-sized worlds. To accomplish this, it would employ a breathtaking piece of engineering, a separate, flower-shaped spacecraft called a starshade. This starshade would fly tens of thousands of kilometers in front of the telescope, perfectly positioned to block the blinding glare of a host star, revealing the gentle light of a small, orbiting planet. The heart of the debate within the scientific community is a classic question of strategy. Do you build the giant, versatile explorer that can advance all of science, or the specialized hunter designed for one of humanity's most profound questions? The technological challenges for both are staggering. LUVOIR requires perfecting a complex, multi-segment mirror and an advanced internal coronagraph that can cancel starlight with unprecedented precision. HABEX demands an exquisitely coordinated orbital ballet between two separate spacecraft, maintaining a formation with millimeter accuracy over vast distances. These are not just missions, they are the proving grounds for the tools that will ultimately let us see another pale blue dot. The choice we make will ripple through the next century of discovery, determining whether our first detailed look at a habitable world comes from a grand universal observatory or a dedicated planetary hunter. This monumental decision about how we search for life finds a parallel in missions designed to explore the very substance of reality, to understand the nature of the space through which all light must travel. The universe holds its breath and then screams. For a fleeting moment, a pinpoint of light outshines every star in its galaxy, a final, cataclysmic declaration from a dying star or the furious collision of stellar corpses. These are the transient events that flash and fade across the sky, and catching them requires a dedicated cosmic sentinel. The transient high-energy sky and early universe surveyor, or Theseus, is a mission concept designed to be that watchful eye. Its sole purpose is to scan the heavens for the most violent and ephemeral explosions, with a special focus on the most powerful of them all, gamma-ray bursts. When it detects a flash, it will rapidly determine its precise location and then pivot to observe the event across multiple wavelengths of light, from infrared to X-rays. This quick and comprehensive characterization is vital because the most valuable data often comes in the first seconds after the initial burst. Theseus would then act as a cosmic air traffic controller, instantly broadcasting an alert to a global network of observatories. On the ground, massive telescopes would swing toward the coordinates, and more exotic detectors, like those built to sense gravitational waves or neutrinos, would fine-tune their own search parameters. This coordinated effort, known as multi-messenger astronomy, allows us to study a single event through different senses simultaneously, building a complete picture of the physics at play. One of the mission's most profound goals is to look back to the very end of the cosmic dark ages, a time when the first stars began to ignite. Scientists believe the deaths of these primordial giants produced gamma-ray bursts of unimaginable power. By detecting these ancient flashes, Theseus would illuminate a chapter of cosmic history we have never before been able to observe directly. It would probe the conditions of the early universe and test the behavior of matter under the most extreme gravitational forces imaginable. Each brief flash is a messenger from the edge of reality, and by catching them, we compile a new understanding of the cosmos in its most dynamic and volatile state. This relentless monitoring of the sky's most fleeting events reveals a universe of constant, dramatic change, a narrative written in sudden flashes of light that compels us to ask what quieter, more subtle signals we might be missing in the dark. A dusty bootprint sinks into the gray soil, a mark that will remain untouched for millennia. This is the goal of the Artemis program, a human campaign to move beyond brief visits and build a lasting home on the moon. This endeavor is far more than a single mission. It is a sprawling architecture of next-generation hardware designed for permanence. The colossal Space Launch System rocket will hoist the Orion crew capsule into deep space, while new lunar landers will ferry astronauts between orbit and the surface. At the heart of this effort is a fundamental shift in strategy. Instead of planting a flag and leaving, Artemis aims to establish a sustainable outpost, with astronauts living and working on the lunar surface for weeks at a time. They will conduct geological fieldwork at the mysterious South Pole, a region bathed in perpetual shadows that preserve ancient water ice. This ice is not merely a scientific curiosity, it is the key to survival. By learning to extract and split this water into hydrogen and oxygen, we can create breathable air and, more importantly, rocket propellant. This practice of living off the land, called in situ resource utilization, transforms the moon from a destination into a gas station for the cosmos, a necessary stepping stone for the far more ambitious journey to Mars. NASA Administrator Bill Nelson often describes the moon as our proving ground, a place to test the technologies and learn the skills we will need to survive on a world tens of millions of miles away. The scientific return will be revolutionary. Human intuition and flexibility allow for real-time decisions no rover can match, selecting the most promising rocks to bring back to Earth. These samples from the lunar South Pole could hold a frozen record of the early solar system. The far side of the moon, permanently shielded from Earth's radio chatter, offers a pristine silence for radio telescopes to listen to the faint echoes of the universe's dark ages. Artemis is the foundation of a new chapter in human history, one where our species learns to thrive beyond the cradle of Earth. This establishment of a permanent lunar base is the critical, non-negotiable first step toward a future where human footsteps mark the red sands of Mars. A chemical map of 1,000 alien worlds is being drawn not from single profound portraits, but from a vast census of atmospheric data. The RIEL mission, developed by the European Space Agency, embodies this statistical revolution. Unlike observatories built to stare intently at a few promising Earth-like candidates, a RIEL is a surveyor designed to glance at a vast population of exoplanets as they cross the faces of their stars. During each transit, a tiny fraction of the star's light filters through the planet's thin atmospheric veil. Our RIEL's powerful infrared instruments will capture this faint, altered light and split it into a spectrum, a unique barcode that reveals which gases are present. By repeating this process for 1,000 different worlds, from puffy, hot Jupiters to dense, rocky super-Earths, the mission will build the first comprehensive database of planetary atmospheres. This massive dataset will answer questions that are impossible to address with a handful of examples. How does the intense radiation from a red dwarf star strip away the atmosphere of a closely orbiting planet? What is the chemical link between a planet's final composition and the specific disk of material from which it was born? A RIEL will look for overarching patterns, identifying common atmospheric recipes, and just as importantly, the strange outliers that defy our current models. This transforms our understanding from a collection of individual curiosities into a true science of comparative planetology. We will no longer just know what one or two exotic worlds are like. We will begin to understand the rules that govern an entire galaxy of planets, placing our own solar system's quiet, stable giants and small, rocky worlds into their proper cosmic context. This grand chemical survey provides the essential background against which we can identify the truly rare and promising worlds, the ones whose atmospheric whispers might one day tell a story of life. Two faint signals, still whispering after nearly 5 decades, continue their journey into the void. The Voyager interstellar mission is not a new endeavor, but its enduring legacy is the very foundation upon which all next-generation missions are built. These twin pioneers, Voyager 1 and Voyager 2, have long since completed their grand tours of the outer planets, yet they persistently phone home from a realm no human-made object has reached before, true interstellar space. The data they stream back is sparse now, a faint trickle of information about the magnetic fields and cosmic rays in this uncharted territory, but it provides the only direct measurement we have of the galaxy's environment beyond the Sun's influence. This priceless information is creating the essential baseline for the future interstellar probe, telling engineers exactly what kind of conditions that bolder mission must be designed to withstand. The staggering longevity of these spacecraft is a triumph of foresight and robust engineering. Built with the computing power of a modern car key, they were engineered for reliability above all else, their systems hardened against radiation and their power sources designed to last. Their endurance has fundamentally reshaped our expectations for a mission's lifetime, proving that with careful design, our robotic emissaries can operate for generations. The lessons learned from their construction, their navigation, and their slow, graceful aging are now being encoded into the blueprints for every deep space mission that follows. We are learning to build explorers that are not just powerful but persistent. The Voyagers remind us that the most profound transformation in our understanding does not always come from a single, shocking discovery, but often from the patient, long-term accumulation of data from the frontier. Their quiet, ongoing transmission is a promise that our reach into the cosmos is only beginning, and that the greatest journeys are those that continue to teach us long after they have vanished from sight. The true power of these missions emerges not in isolation, but in their profound conversation with one another. Each explorer speaks a different language, from the chemical whispers of a RIEL to the space-time tremors sensed by LISA, yet together they are translating the same cosmic epic. The galaxy-wide sensors from the Roman telescope provides the essential map that tells LIS where to listen for the most titanic black hole collisions. The atmospheric profiles of 1,000 worlds from our RIEL will inform the Habitable Worlds Observatory which single, pale blue dot deserves its most intense and focused stare. This is not a random collection of projects. It is a carefully orchestrated symphony of discovery. The search for life is guided by planetary science from Dragonfly, which is itself informed by the chemical origins traced by the Origins Space Telescope. Every answer one mission provides immediately generates smarter, more profound questions for the next. This synergistic push across all fronts of science, from the quantum behavior of matter in Lynx to the vast cosmic structures in Athena, represents a fundamental shift in our approach. We are no longer just looking at the universe, we are learning to diagnose it, to understand its underlying physics, its history, and its potential for life as a single, interconnected system. The relentless innovation required to make this possible, from starshades flying in perfect formation to detectors chilled to near absolute zero, does not stay locked in observatories. These technological leaps inevitably ripple outward, driving progress in medicine, computing, and materials science for everyone. This grand tapestry, woven from 25 threads of human curiosity, reminds us that our deepest questions about existence are not separate. They are part of a unified quest, a collective reach for understanding that pushes the very boundaries of the possible and forever redefines our place in the story of the cosmos. We stand at the threshold of a new era where the questions that have haunted humanity for millennia are finally becoming answerable. Each of these missions, from the drone flying on Titan to the telescope listening for the birth of the universe, is a testament to a single, powerful idea: our innate need to understand the cosmos we inhabit. The journey from a quiet star's habitable zone to the silent void of interstellar space charts a course of relentless curiosity. These are not merely machines of metal and glass. They are the instruments of our collective awakening, designed to translate the unknown into the known. The data they will return promises to rewrite our textbooks, not with speculation but with evidence, transforming our place in the universe from a solitary assumption into a detailed cosmic context. As Carl Sagan so beautifully reflected, somewhere, something incredible is waiting to be known. That incredible something is now the target of our most ambitious searches. We have the extraordinary privilege of being the generation that gets to watch this unfold, to see the first atmospheric readout of a twin Earth and hear the first gravitational chord of colliding black holes. This is an invitation to you to be a part of that journey. Follow the progress of these missions, engage with the stunning images and discoveries as they are released, and share your own sense of wonder in the comments below. If this vision of the future excites you, subscribe for more explorations into the frontiers of knowledge. Together, we will watch as humanity's understanding of the cosmos is utterly and profoundly transformed.